Welcome to our 7th class. Let's start with what we have so far. So far we spoke about the Schrödinger equation, right? That was the thing? Yeah. So we spoke about the Schrödinger equation, we spoke about different potentials. We spoke about the free particle, we spoke about the infinite potential well. Infinite potential well had signs, right? An infinite amount of signs that was reminded us of the Fourier series. Then we had the scattering problems, right? In scattering problems we spoke about current, right? About J. And then we defined transmission and reflection. That was fun. There we required the wave function to be continuous and for the derivative to be continuous. So we had these things and we had these things. When you have this, that's split into two. To this and to this. Now I wish to discuss another case, which is the case of finite potential. Well, this is going to be the topic of today. Did you speak about it in class? I know you guys spoke about harmonic oscillator. Did you ever speak about finite potential well? Okay, so this is what we'll do today. It's going to be fun. There's going to be only one specific tool that's going to be different in the way we approach things. However, the result is going to be a little different. What we have now here is v of x is equal to minus v naught, where x is between 0 and L, and 0 else. What does it look like? Well, this marker is tired. This is what it looks like. This is my potential. Now, what is my energy? If my energy is here, this is E1. If my energy is here, so it is simply a scattering problem, just like before. What I have here is a wave coming in. Here it splits into two. This one here splits into two. And that's it. Just like before. Beforehand we had it with a finite potential barrier, finite potential step. We spoke about it this way. And now I'm talking about this, which is not very different. What would be the solution here? Well, here I have e to the ikx. Here we have psi is equal to a e to the ikx plus b e to the minus ikx. Here we would have c e to the I. It won't be the same k, right? Because here I have a different energy. Qx plus d to the minus I qx, and here we have again d, not d. So we have here, aha, we have this disgusting thing. I would have here f e to the I kx plus 0, because there's no wave coming back, and I would require continuity of stuff. I would require continuity of the derivative, etc. Here k would be square root of 2me over h bar. And here q would be square root of 2m times e plus v naught over h bar. Are there any questions on this? Did I do it too fast, the k and the q? Or did we see it enough times that it's easy? We said it enough times that it's easy? Good. So now I do, I don't know, a plus b. I just want to make sure that the two conditions are kept here, two conditions are kept here, and then I can say that r would be, I don't know, b over a squared, and t would be f over a squared. Of course, here I'm supposed to have times q over k, or k1 over k2, but here they're both k, right? So this would be the transmission and the reflection and everything, and this is exactly what we saw last time. Boring. what will be more interesting? We're going to talk about an energy lower. I'm going to have an energy here. This is going to be entirely different, right? Let's do this.
But you need to start inside the potential, right?
Yes.
You cannot start.
So what I would have here now, I can actually go down here so you can also follow here. Is this fun for you? It's also here. Does it help anyone? Good. So this is what I would have here, and I would have to, and this would be well, that's exactly what I just did. Is it clear why it's E plus V naught here? Yeah. My energy is, because I had,
from the Schrödinger.
I had this. I have this. I move this to here, so I get minus I bar squared over 2m psi double prime is equal to E plus V naught psi. Okay, but now we're going to talk about energy lower than this. So here, I can still treat it as a free particle. So I get this with a different Q. Now, E2 is going to be minus a certain E. Right? I can write this way. E2 is negative. So what I would have here is you can put this here, right? Because now the energy I have here is lower. It's not this, it's only this. The difference between V naught and E. And if I have, well, this is my Q. However, here I would need to have real exponents.
Right.
Now, as far as I see it, I did this too fast. Unless every single person here tells me that it was clear, I will explain to you why it's real exponents. Is it clear why it's real exponents? Maxim, Joseph, Eliao, Paula. I'm sorry. Wait a second. Hi, Kai. Okay. You were something with L. Now you had an L in your name. What's your name again? Doran. Okay. And? Kaha. Is it clear why it's real exponents?
Yes.
Is it clear? Is it clear? No, it's not clear. It's clear. Okay, so here we have real exponents, and then what do we need to do? Again, we need to show that the wave function is continuous and the derivative is continuous. Same problem, different solution, because I have a different energy. Same potential, different solution, and here, this energy, I would consider it as a bound state. Right. Because it is confined, it is locked in this well, right? Now here, we saw that you could have many bound states. You could have this one, and you could have this one. You can have an infinite amount of those, right? Here, we're going to get a quantization, okay? And this is what we're going to learn today about. We're going to see that maybe we have here, for example, one energy possible, another energy possible, and the third one is going to be already a free particle. There's going to be a specific set of energies that are allowed here, and finding them would be through a transcendental equation that we're able to solve either numerically or graphically. As I teach it, you'll understand what I just meant. Okay? May I erase the whiteboard? Okay, first I want to see here. So this is the solution here. I got A, B, C, D. And these are my K and my Q. And now we're going to do an actual example. The example is going to be half infinite potential well. What does it mean? The potential we shall be discussing now is going to be very mean. This is the potential. Here it's infinite. Here psi is 0. I'm going to want to have an energy here. So here, psi would be AE to the I minus IKX plus BE to the plus IKX, right? And here I'm going to have a decaying exponent. This is the solution that I'm expecting. So first let's write what V is. V of x is, if x is smaller than 0, it's infinity. If x is between 0 and L, it shall be 0. And if x is bigger than L, so it's going to be a positive V naught. And I'm going to try it. I think there's another marker here. Just like any physicist would respect himself, I had a whiteboard in my house, and my son decided to use the blue marker. Sorry. Started green. So this is my V. Mouse. So the solution I'm expecting is this thing. I can write the Schrödinger equation in each area separately and solve it for each one.
There is a problem. I'm not sure it's true that under the square root of u you have minus e plus v0. I got something else.
Okay, what depends here is where do I put the 0. Beforehand I put the 0 here, and this was minus v naught. Yay! Thank you very much. You're so very kind. Beforehand, I said that this was here v equals 0, and here v is equal minus v naught.
Now it's the other way.
Now I decided here is the 0 and here is the plus v naught. I only didn't say it. Right? There's all those things that teachers do. They sweep between the right hand side and the left hand side without saying it, right? Because it's very easy. But when you don't do it yourself, it's not. And so, I can just skip to the solution here. No. Go down. Here. So this is the solution that I'm expecting, where psi of x will be, if x is smaller than 0, then it's 0, because otherwise there's no, like, you can see the development of it in this PDF that's in the Moodle. However, you all seem pretty comfortable with these concepts, so I'm allowing myself to spend more time on other things. Here I would have, where x between 0 and L, I would have ae to the I kx plus be to the minus I kx. Here I define, here's v is 0, right? Therefore k is going to be the square root of 2me over h bar. And here I would have de to the minus I qx plus ge to the plus I qx, only there's no I here, because these, as I said, are real exponents. This should be 0, because otherwise the wave function is not normalizable. And what would be q?
It's the square root.
Here I'm going to do plus v naught times psi is equal to e psi. So h bar squared over 2m psi double prime is equal to, I'm moving the V naught to the other side
Right.
and putting a minus on both. So here I have minus V naught minus E times psi, right? Any sorry. Wait a second. No, yeah, this is a bit plus.
Yeah.
Right? Very good. Thank you. Something didn't seem right. Now I know that my energy here is positive or negative.
Positive.
Here's V is 0, and here is V equal to V naught. So my energy here is positive. But it's smaller than this. So this thing here is positive. Do you see that it's positive?
Yes.
Ben, do you see that it's positive?
Of course.
Are you positive?
I'm always positive.
Good. So if this is positive, so my answer is, of course, real exponents and not imaginary one, where my Q is going to be the square root of 2m times V naught minus E over H bar. So I'm going to write it here. 2m V naught minus E over H bar. And now may I erase this white, this black part? No, I'll erase it soon. So this is my psi. Now I want to make sure that I A, B. Okay, they wrote here C. Wait. Oh, then we're good. We're good. This is C. But it doesn't matter. Okay, now I want to make sure that the boundary conditions are kept. How do I do that? Just like before. Psi of 0 must be psi of 0.
Which is 0.
Therefore, 0 must equal to A plus B. And I know how to solve this. That means that A is equal to minus B. I'm good at that. Now I have the derivative one, which is that.
The psi dot T equal to the psi.
Wait a second. Yeah. Now let's do continuity here. I know that A. This one. 2 I want psi of L minus to equal psi of L plus. Therefore, AE to the IKL plus BE to the minus IKL. Instead of B, I wrote here minus A. Is that okay?
Yeah.
Yay. This must equal DE to the minus QL. This is simply 2A sine KL. Am I correct here?
You're missing an I, right?
Very good. 2AI. I probably said this before, buddy, but it's very important as a teacher to sometimes make mistakes that are very clearly intentional. Because this one, when I make not intentional mistakes, then you can think that I. Anyway.
And we can also take the wave function to infinity, right?
What?
We can also take the wave function to infinity and say that it has to vanish.
Yes, this I did already here by canceling the C. Now what we do here in this document that I like to follow is that we call this thing here A tilde. I can do that, right? I'm allowed to do that, why not? This is equal to D e to the minus QL. Now let's do the derivative of that, okay? 3 would be the psi prime of x equal L minus should equal to psi prime x equals L plus. This whiteboard is getting a little confusing, so I want to rewrite this now in my most compact way for now, okay? Where x is negative psi 0, here I got a certain A tilde sinus KL, right? This is what I got because of this. Sinus KX, I meant. And here I got DE to the minus QX. It's, by the way, of course, I allow myself to a tilde to swallow the 2, the a, and the I.
The last one is when x bigger than L.
What?
This is dE to the minus qx when x bigger than L.
Oh, yes. You happy now?
Yes. No, I'm just getting.
Are you happy now?
Yes.
Good. And now, I got a well, I didn't do yet the derivative of this at x equals L is equal to the derivative of that at x equals L. Let's do this. The derivative of sine is a oh, good. So I have a tilde times k cosine kx is kl, sorry, is equal to the derivative of that, which is minus q d e to the minus kl. This is the continuity of the derivative. Let's rewrite this line here, okay? I have here a tilde sine kl is equal to
the
dE to the minus ql. Now, some of you might think that this is not very helpful, because what do I do now? This is actually where I was aiming for, and this is always going to be the case when you have finite potential wells. When I get here, this was my goal. From here, I just need to understand what the solution meant. What I'm going to do now is I'm going to do 1 divided by 2. Meaning I have here 2, what? I'm going to do 1 divided by 2. And doing this, I will get rid of both constants. Meaning I could solve this isolating a from here, plugging it in there. I could do that and find a, but I'm not interested in that. What I am interested in is understanding the solution. So let's see what happens now. A cancels each other out. I have here k cotangents of kl is equal to
minus q.
q d.
Why did you not include this?
No d. Minus q, right? All right. So cotangents of KL is equal to minus Q over K. Hey, that's exactly what it says here. Now I'm happy. This was my goal. I got here a transcendental equation between Q and K, which are the solution of the Schrödinger equation in all my region. I'm not interested in finding what is A. It wasn't asked what is the chance of finding the particle on the right side. I just want to know what are the energies possible. This is usually my goal at problems of finite potential well. How do I solve this equation?
Numerically.
I could solve it numerically, but there's another way.
Graphically.
Yes, graphically. In order to solve it graphically, I'm going to do two things. First of all, I want to go back, instead of writing K and Q and, well, K and Q, I want to rewrite this, okay? I have here cotangents of, what is KL? It is square root of 2me times L over h bar. This equals to minus this divided by that.
Which is
So h bar and h bar cancel each other out.
and 2m.
And here also 2m cancel each other. I have here v naught minus e divided by e. Cotangents of square root of 2me times L over h bar is equal to minus the square root of v naught divided by e minus 1. Am I correct? afraid I did a mistake here. No, okay. Now, I'm going to make an odd choice, and I'm going to call this thing here theta. Okay? And this I want to call something over theta. So I'm going to call it theta naught. I'm going to get here cotangents of theta is equal to, I see here that E, the theta includes the square root of E. So within the square root, this is theta squared, right? I want to have here theta squared over something, and call it theta naught squared minus 1. Theta naught turns out to be, not surprisingly, the same thing only with V naught.
Right.
Is there a way to wash it? Just put it in a washing machine or something?
It should be a minus.
It should be a minus.
Square.
Yeah.
What?
Before the square root.
Before the square here. Thank you. So I can write here theta is square root of 2me times L over h bar, and theta naught is exactly the same thing, only with V naught. And this is my transcendental equation. How do I solve this thing? It doesn't work. You mean I'm not typing correctly? Not gonna be right.
Got
Okay, and here I have minus the square root of V over x Okay. This is the way to solve this thing graphically. I'm plotting the left-hand side and I'm plotting the right-hand side as a function of theta. And I write it for different values of theta naught. Okay? So I can write it here. So you can see here for two different values of theta naught, right? And my solutions are going to be where these two graphs intersect.
and in the positive side, right?
A second. I should share the screen for whoever's going to watch this. I don't share screen here. Okay, so what we have here in red is the left-hand side, which is cotangents, and what I have on the green and the black is the right-hand side, which is the minus square root of something over something squared minus 1. Is there a solution? I can see that for the green there's no solution. These two things are never equal. For the black there is one solution. What I expect is that if I take V naught to be bigger and bigger and bigger and bigger,
There will be more solutions.
you'll have more solutions, right? Because it's getting closer to the case of, I'm looking as if it was there because it was there before, to the case of the infinite potential well. Let's see if that's what I get. I'm going to increase V. Ah, they're both moving to the right. Right? Now you have two solutions. Now you have three solutions to the green one. Does this make us happy? Good. Now for this given for this given V naught, it can play with the energy. Let's say I have a specific value of V naught. This is the height, right? I can play with the energy. Can I play with the energy? What happens if I play with the energy? If I make the energy higher, then I get more solution. I'm not sure what this here means. Just a restate. No point in this. So this is how I plot my answer. And here there's cases where there's zero answers, maybe one answer, two answers, etc. Okay, here there's one answer for the green and two answers for the black. Two solutions for the black. So I can ask you, for a given potential well, how many bound states are there? Now you know how to plot this. It's not fun, right? But you can see exact. You know how to plot cotangents. It's always the same. It's cotangents. The divergence at cotangents is 1 over cosine. Pi over 2. Pi over 2.
Pi over 2. It's like tangent.
The sinus חלקי cosinus. Cosine, let's say pi over 2. Pi over 2 is
over 2 and...
But it's not pi over 2.
No.
Oh, because I have here a certain number of the thing. Wait a second. Why does it not diverge here pi over 2? Why does it diverge here pi?
Cotangents is like tangents, but it's inverted and it's moved. So the width, the distance between two asymptotes should be pi.
Why not pi over 2?
Right, because
oh, yeah.
it's right, it's cosine over sine. It goes in sine.
So you know how to plot this red graph. You know how to plot the square root, right? The square root would look like this. Meaning you know how to plot the square root. You know how to plug in different numbers and plot those things. And this is how you plot this. So this was the case of half finite potential well. Meaning on one hand on the one side it's finite, on the other hand it is infinite. Now it's quite cool to show. I wasn't planning on showing because I thought, for some reason I imagined that Richard showed it in class, that if the well is finite on both sides, then you for sure have one solution, one bound state. Meaning here there's cases if this thing is too shallow, so there's zero solutions, right? It's impossible. It's not allowed to have a bound state.
Right.
It doesn't work with the Schrödinger equation. However, if you plot the case of finite potential on both sides, then you will always have at least one bound state. Should we show it?
The difference between the green and the black
Is different values of tetanot, different values of V naught.
Why does this calculation give? Why does it give just the bound state? Okay, because you assumed it at the start or something.
Yes, because I assumed it at the start. Because I assumed it. You're asking correctly. I assumed this here. Here I wrote real exponential and not oscillatory ones, not imaginary ones. Where else do you see it? You see it here. If E is bigger than V naught, then what do you have here?
If E is much bigger.
If E is bigger than V naught,
Oh, then it's
It's an imaginary number.
and this is imaginary, and this a real thing is never going to be equal to imaginary thing.
You have to rewrite the solution from the beginning.
Yes. Which I'm wondering now if I should do for the case of a full potential, of a finite on both sides. I don't have enough self-confidence for it. I think I'll just move on with the thing.
If in the test you ask the bounds, you say you can't answer this. How I know how many I can have without decimals?
No, without decimals, you can still plot it. It simply take you 10 more minutes. You know how to plot cotangents?
Yes.
Do you know how to plot square root?
Yes. And
Yes,
just
now-
see for a different value.
Yes, you do square root. You know how to plot a square root. You know how to plot a square root of
Minus, yes.
of something over x squared minus 1. Then you do the same thing of 2 over x squared minus 1. Which is exactly what you have here. All this is also here. You have here these graphs. It tells you exactly For the graphical solution, follow a few easy steps. Plot the left-hand side. Here it's cotangent theta as a function of theta. Plot the right-hand side as a function of theta for different values, for different choices of theta naught. Play around with it. The points at which the two plots intersect are a solution. Okay? Now I can also find the eigenfunction. I'm not very interested in it, but I could ask you, what are the chances of finding the particle on the, like here? Here, it is decaying exponentially, right? The chances of finding the particle on the left would be P of x bigger than L would be the integral of dE to the minus qx squared dx from L to infinity, right? I know everything besides d. I need to find d for that.
It's from x bigger, right.
This is the chance of finding the particle anywhere here. I know how to solve the integral of an exponent. That's not so hard. I do need to find d. How do you find d? Well, we have this. They can. Is this what we're asking here? It's not what we're asking here, right? Instead of d here, I can write a sinus kl times e to the plus kl. Let's rewrite it here.
But you need to do the integral over all space.
Yeah, I did the integral from L to infinity.
But to be normalized.
Oh yeah, I knew. Yeah, you're right. In order to find a, I need everything to be normalized.
Right.
So I can say that. I need a black marker. Psi. Well, from here I can extract that d is equal to a tilde sine kl e to the ql, the positive ql. So psi of x is equal to, here it is 0. Here I have a tilde sine kx. Here I have a tilde sine kl e to the ql times e to the minus qx. And now in order to find d for this, I need to find a for that. In order to find a, I need to normalize. In order to normalize, I write 1 is equal to integral of psi squared dx from 0 to infinity. I have no psi at 0, which is a tilde times integral from 0 to L over sine kx squared dx plus the integral from L to infinity over sine kl squared e to the 2 q L minus x dx. And this is not so bad. This is something that's legit for me to give you for homework, right? You put it in a I hope you don't solve it yourself. I'm going to repeat myself for something that I said in the past. If you know how to solve these integrals by yourself in the exam, there's no point in you wasting time on it and the homework. If you do not know how to solve these integrals, then please do spend the time doing it yourself. Okay. Here I have the solution. It's really not interesting. You can follow it. Oh, I forgot to stop sharing the screen. So here I have the solution. I need to do this, and I get a certain beautiful value of A. Doing this, we finish the case of half finite potential well. And I'm debating if I should do the full finite or not. What should I do? Well, I think we'll do this. Now we're going to have an entirely different potential. We're like half time soon. Yeah. Take 120 seconds break. Enjoy. Want to see all your phones coming out? Come on, you need to breathe. 120 שניות. 120 seconds. Meanwhile, Eliyahu is going to tell us where he grew up. Sorry for asking. So apparently, almost every country has a city that's like the joke of the country. That doesn't exist. Nothing happens there. It's not interesting. Is there one in Mexico?
Yeah.
Which
No,
one?
Like skull.
Okay, so there's a place. So the place in Israel, the people laugh at all the time, but it doesn't exist. It's not interesting. If we need to, it's not right. It's Petah Tikva. Chinese students. Is there a place in China that you know of that is?
Well, you know, there is a whole province. We call it Henan. You know, it's not not everyone think it's boring, but there are many crazy things happening. There are many weird people.
So it's a place you don't want to go to.
Yeah. How it's called? Henan. Yeah.
So if something bad happens, you say, "Oh, for sure it happened there."
Yeah, these people they are doing crazy things, and we can understand them.
כמו אשקלון בישראל.
אשקלון? פתח תקווה.
פתח תקווה היא עיר רעה. אשקלון היא עיר מלאה באלפים.
In Mexico, in Tlaxcala, there was news because in 2017 they inaugurated the first electrical stairs.
Stairs?
Like, you know the.
Excavator?
Hmm?
Excavator?
Oh, stairs.
Yeah,
Oh. When?
2017. And it was news. The mayor of the city, the mayor of the city went to the inauguration.
Okay. So, stop sharing. There's only so much I can share with others. Now we're going to do another case. It's going to be a potential of the kinds that you already saw, but we're going to have here a specific trick of solving it, which would have to do with the parity of V. This is my introduction. Now let's start with what we actually have. Our potential is going to be, I had a red one. Oh, here it is. Our potential is going to be very mean. It's going to be infinity here. Here x is minus L. Here x is L. And in between I'm going to have a delta barrier. This is very, very not straight. This is better. And this is my V. So, of course, psi here would be 0, psi here would be 0, and the chances of finding the particle here would be probably the particle exactly here?
0.
0, also the width of the thing itself is 0. But we're going to require the wave function to be continuous and the derivative to jump. Remember? Same trick as we had last week, same trick as we had in the homework.
It cancels out some of the solutions of the infinite square one.
I'm not sure what you mean, but we'll see. It's going to be fun. Okay, I can write here v of x is equal to beta delta of x, where x is smaller than L and 0 and infinity else. Okay, wherever the absolute value of x is smaller than L, meaning between minus L and L, so all I have is a delta function in the middle, and then I have this. One of the questions that Eli Balkai, who's the professor I'm used to, likes to ask here, just to make sure you understood, is what are the units of beta?
It's
Energy times
right.
So let's see. 1 is equal to the integral of delta of x dx.
So
So delta of x is 1 over meter, right? if I have beta times delta is equal to energy, so beta is going to be energy over delta. It's going to be energy times meter.
It's in the homework.
Oh, there is this thing anymore? Okay, good for you. And did you?
Yeah.
Apparently there was a point in doing it. So here, I'm telling you that it's more convenient. Instead of writing here e to the I kx, it's more convenient to write it as sines and cosines. So I'm going to write here, on the left-hand side, psi of pi is equal to, where x is between minus n and 0, not a good planning of the whiteboard, psi would be, if it be a cosine of kx plus b sine of kx, wherever x is between minus l and 0. However, when x is between 0 and l, it's going to be c cosine kx plus d sine kx, or of course k is the square root of 2 me over h bar. That's what it says here. And the trick now again, I need to show that when x is equal to 0, everything is equal, everything is continuous, where the derivative should jump, etc. But there's a big trick here. And the trick is one specific trick. When v of x has a defined parity, odd or even, psi must be odd or even. I'm going to use this because I'm going to solve now assuming that the solutions are odd. Then I will solve assuming the solutions are even. And the solution is going to be this or that.
Or this solution is.
Doing this now is complicated. This problem is a little hard to solve. I have here 4 constants. I need to show that what are going to be my equations, okay? I'm going to have here psi of minus L is 0, psi of L is 0, psi of 0 minus is equal to psi of 0 plus, and psi prime of 0 plus minus psi prime of 0 minus is going to equal something that I keep forgetting. Okay? 1, 2, 3, 4. 1, 2, 3, 4. Right? It's possible to do that. It is hard. So it'll be easier if I treat the function as even, or if I treat the function as odd. Okay? It's going to solve me some hard work. It's going to save me from some hard work. So we're going to start with the even ones, okay? Even wave function, that means that psi of x is equal to psi of minus x. So this means that I can replace this with a and this with d, right? This way to be equal at all times. How can I also show it? I can just, well, I think that's clear enough. The way Yaakov, who wrote all these beautiful PDFs, shows it is replacing here x by minus x. He takes this, replace everything by minus x, and you're supposed to get the same thing.
Right.
So this, cosine of something.
Of minus something.
Wait a second.
It's
no,
the
I made a mistake.
minus.
We're gonna do it. We're gonna do it more slower. We're gonna do it a little slower because apparently I got confused myself just now.
You use the parity operator.
Psi of x is a cosine kx plus b sine kx. Did the Richard spoke about parity operator? Okay, so you've seen those things. Z when x is positive. Therefore, if I just replace the x, replace x with minus x, I get here a cosine of minus kx. Hey, for the cosine it doesn't matter. I can just erase this plus b sine of minus kx. But sine is an odd function. I can replace this here with a minus here. If I want this to be equal to that, I want this, sorry, to be that. I did a mistake. I started with it. Whatever, you get the point. A is C and B is minus D.
Right. It's okay. You just.
I did, yeah, it actually is okay, yeah. I just did, all I need to do is do this. Now I'm good. I took this thing, and then I flipped x with minus x. I'm supposed to get C cosine plus D sine. C cosine, so A is C. I'm supposed to get plus D sine. I got a minus B sine. So B, so D must equal to minus B. Okay, let's write it here then. I got here A, and here I got minus B. Now let's make sure all these conditions are kept. It didn't use even one of them, right?
What after Vx is an odd function where the wave function have a parity.
I think so. I might be wrong. I think it does.
I'm not sure because I only improved that when the Vx is
Only for even.
I think so.
Okay, so you guess you're right because I'm not sure, and you seem more sure than I am. So when it is specifically even, not odd. Okay, what I wrote before, that when V naught has a clear parity. So Lukian, no, again, Julan. Okay, says that it's this trick works only when V is even, not odd. Sorry for misleading you. So let's see what happens at let's start with this. Psi of x equals minus L is A cos. I'm supposed to write K times minus L, but it's just like writing KL plus B sine K minus L. So I'm writing here minus instead. This must equal 0. Therefore, I don't know, A cosine KL equals to B sine KL, and I can include that B is equal to A cotangents of KL. Good. There's a fun thing. As you see here in the document, he's trying to be very, very slow. Writing psi like this every time from the beginning. Let's move to the discontinuity of the derivative. The way to the discontinuity of the derivative, it's always confusing. And where do I put my limits, and what is plus and what is minus? So we always start again from the Schrödinger equation.
Why you go straight to the discontinuity and do not go through the second and third equations?
This one is going to give me the exact same condition. Psi of x equals L, because it's parity, right? If here it's 0, then here it must also be 0. Should I show it, or it's...
No.
Okay. You want to first do this? We can first do this. Will it make you happy?
No.
No, it will not make you happy? Okay. Let's do the derivative. Honestly, because it's already the same. If you do this, it doesn't add you any information. What happens? Psi of 0 plus is equal to psi of 0 minus. It means that here I have A cosine. Sorry, on the left hand side I have, this is the right hand side. Psi of 0 minus is equal to psi 0 plus. Because doing right and left hand of the equation, and right and left side of the potential is confusing. So I'm going to try to be inconsistent here. The left-hand side is psi minus. I use this. Sine of 0 is then
0.
and here I have
1,
A. When I move to the right-hand side, I have here sine of 0 is 0, and here I have
Because
A. So it doesn't add any information because I already used it by the parity thing.
when you use the parity, you get rid of two variables, and that's it. Conditions 2 and 3. You just solve 1.
Wait.
You have 3.
Exactly.
Just asking, is the final answer going to be if there wasn't a delta, right? Then you would have sines with different frequencies. Would the effect of delta be just canceling out the odd frequencies?
What I expect is that for that, we'll see that the end, also at the end of this document. When beta, I expect, and that's what we'll get, is when beta is 0, I'll just get the odd and the even things of a infinite well with size of 2n, right? It's not that, it's 2n, just need to replace it. However, when beta is very big, I expect to get here one infinite potential well and one another. Only that they're correlated because positive and negative, because parity. But I expect to find here signs and here signs.
In this case, you won't have only sines, you will also have cosines, right? Without the delta. If you wouldn't have the delta, you will have cosines and sines.
Yes, correct. I'll just explain what Joseph said. I said that here we have only sines and we have, in the case of infinite potential well, we have sines. This is 1, this is 2, etc., right? However, this is when this is between 0 and n. I can write the exact same thing. I did not give you this at the homework, did I?
No.
So this is something that's, sometimes I give as homework. Do the exact same thing, only here. So you can either translate these solutions to this, or start all over again. Of course, you're supposed to get physically the same solution. What will you get? Either this, which I call cosine, right? This is a cosine. Or this, which is minus sine, but whatever.
Right.
So when you do it symmetrical around the 0, you get sines and cosine. Sine, cosine, sine, cosine. Every solution is going to be, you're going to alternate. All the odd ones are going to be sine, and all the even are going to be cosines. So this is what Joseph is referring to. It is one of the solutions we're going to get here. Derivative. We get here, number 4. And we, as I said, we start this. We start the derivative by writing the Irwin equation. So, Irwin says that minus h bar squared over 2m psi double prime plus beta delta of x psi is equal to e psi. Then I do, on both sides, I do the integral from minus epsilon to epsilon dx. What does not contribute anything? This thing. It does not give me anything. It's very counterintuitive because it's weird. This step here is weird. It confuses students every year. Why is it 0? Because psi itself, dx, when dx is 0, is very narrow. This thing is 0. And get here, minus h bar squared over 2m time psi prime of epsilon minus psi prime of minus epsilon plus beta psi of 0 is equal to 0. Let's move this to here and get rid of the minus. And you know what? Let's multiply by 2m over h bar squared. I'm going to have here 2m beta over h bar squared psi of 0 is psi prime of epsilon minus psi prime of minus epsilon.
And psi of 0 is a.
So now I'm going to erase this.
don't understand why the right side of the equation is the ipside, the integral of ipside.
The integral, well, E is a constant, right?
Yes, it's the integral of psi dx minus epsilon of psi.
Psi needs to be normalized. From minus infinity to infinity, it's 1. But when dx goes to 0, then what is the area? Let's say that this is psi, okay? What is the area here?
A professor in Mexico used to tell me that a point doesn't make shadow.
A point doesn't make shadow. Come on. I have a student that asked me yesterday. This is one-dimensional, right? But it has a width. How can you have a real one-dimensional thing? Ever. With atoms.
Right.
It's actually not that much of a problem. Okay, because
I'm sure it's not, because it's mathematical. A line is a mathematical creature, so I can define whatever I want.
It's more the thing that if you want to make the argument that the length of the entire line is the sum of the lengths of the dots, you can't do that because the cardinality of the set of the dots is uncountable.
What?
It's the number of dots that there is so large that you cannot sum it. And when you do an integral, if you look at the precise definition of an integral, it's not exactly a summation. You can't actually formally sum those dots because there are too many. And that's kind of the solution to the problem.
Yeah, just how do you explain this to a 10th grader?
I don't know.
Okay, so I have this, psi prime. This is going to be fun. Here in this document, there's a few mistakes in the document. It wrote here alpha instead of beta, there's a minus that you forgot earlier, or sorry, the I, whatever, different things. Let's see what I have here. Psi prime of epsilon is this. So I get here k, a cosine becomes a sine, right? Now it becomes minus sine. Minus a ka sine k times 0. When I do the derivative of the sine, I get minus b k cosine of 0. All this was psi prime of epsilon. Minus, I need to do the derivative of that. I get here minus k a sine of 0 minus
Plus, right?
I put here big brackets. I hate minuses, so I try to do lots of brackets. Minus k sine 0 plus b k cosine of 0. All this must equal to m beta over h bar squared times psi of 0. What is psi of 0? It is a. Okay, now instead of b, I can write a cotangent because of, well, let's see. First, I want to cancel out
The signs.
the signs. I have here minus b, right? I have minus 2 times b, minus 2 times b,
Okay.
times k because I have k here, is equal to 2m beta a over h bar squared. And now I can cancel out the k, the a's, and the 2's to get a certain solution. Minus now your cotangents of KL is equal to minus m beta over k h bar squared. That is not nice. I'm not drawing this. Does this remind you of something?
The problem with it.
How do you get it?
The transcendental regard what?
So how do you get a cotangent?
From the it was written here before because the boundary condition is
Yes.
zero.
This time it's different because you have infinite domain solutions.
Because what?
I'm pretty sure you have infinite domain.
Yeah, I do have random solutions here.
because you're in an infinite potential well.
Because it's infinite potential. Well, let's show it. Cotangent of x is equal to -1 over x, right? Okay, so you have infinite amount of solution. Oh, should I continue or is it enough?
Wait, why did you add this 1.6?
Oh.
Well,
That
it
means
still
more
works.
1.6.
You're on lifting.
What is this thing? What?
It's
That's 1 over s. What? Oh.
it's minus 1 over x.
That's what I want to do. Okay. So I get here a solution for KL. I can extract the energies from here numerically, whatever. It's not fun. And once I have them, I can write everything like I basically finish my answer, right? I can write here the solutions of this. Let's write those solutions as KL would be Zn. This is a dimensionless thing, right? KL. In general, when I have something inside a cotangent, I expect it to be dimensionless. Also here, I know that Kx is dimensionless, so Zn are my numerical answers of this. So my answers at the end are, what is the relation between K and E? Oh, I had it here. So instead of K, I can write Zn over L. What's my goal now? I want to go back to the energies of infinite potential wells. In an infinite potential well, I had En was equal to n squared pi squared h bar squared over 2ml squared. Right?
But in this case, it's 8L squared.
Here I have 2L squared. Right? So let's see what I get here. Instead of K, I can write Zn over L. So E would be Zn squared h bar squared over 2ml squared. That's what I get here, right?
Right.
Ooh, this seems similar, right? This was for the even solutions. This is the odd solutions. It's gonna be fun. It's gonna be a little odd. I was planning this fun for a while. No? Smiles? You like smiles? It's gonna be odd because it's in. So, when it's odd, I should not erase that. This was E even. When it's odd, I have your C plus D. I want to show that if I take this and change to the minus, so C cosine of minus kx, which is what I wrote here, this is the minus kx, you see, minus D sine kx must equal to, I took the minus of this and I expect to get, I took minus of the argument,
Right.
I expect to find it to be minus of A cosine kx plus B sine kx. Therefore, I'm going to get that C is minus A.
Why minus?
What?
Why minus? In the outside.
Because now I'm looking for the odd solutions.
Ah, okay.
F of minus x
Yeah.
must be minus f of x.
Yeah.
Am I doing it correctly? Yeah. Okay. So C must be minus A. and D is B. Different than before. So let's actually write it here. I'm going to write here B. And here I'm going to write minus A. Oh, wait a second.
Don't say this trick goes only on even.
No. When the potential is even.
Yes.
When the potential is even and the potential is still even. The red here is even, therefore the psi's are either even or odd. First thing I'm going to have to do is actually wash my hands. So, now again, I want to make sure that the boundary condition is kept at the left-hand side. The left-hand side, I'm going to plug in minus L. A cosine of minus KL, I'm going to write just KL, plus B. Hey, this didn't change. Is that the same? I can still just write B is A cotangent KL, right? The next two are still going to be the same. What I'm left with is the thing I just erased before, which is psi prime of epsilon plus minus psi prime of epsilon minus must be 2m beta over h bar squared times psi of 0. Wait a second. You also say that here. Sorry, I did this too fast.
Yeah.
No, not this. Okay, so now I want to show what happens to the boundary condition. And apparently the easiest way to show it is to show the continuity at x equals 0. Psi of epsilon must equal to psi of epsilon plus. Therefore A
Equals minus A.
equals minus A, which means that A must be 0. Was this clear? So I'm going to erase this. Good, now things are easier. We like zeros.
And since we are
also, it makes sense because if you're looking for something for an odd solution, of course you're going to go through 0 here, right? By definition, no?
And you're going to get rid of the cosines that are even and not odd.
Yeah. I'm not sure I follow.
Since we are looking for odd functions,
yes,
of course we are going to get rid of the cosine part. Because it's always a even part of the function.
That makes sense. But so beforehand, why did we have both sines and cosines if we were looking for odd, for even solution?
Let's see. But we end up with only cosine solutions.
No, we had both. We had A sine and B cosine, and we had
right.
So a constant line between them. Because what you're looking for is when I'm talking about odd and even, I'm not talking about sines or sine. I'm talking about odd and even with respect to minus L to L. So I'm not sure your argument is so trivial. Anyway, if A is 0, so this gets a little easier. I get here the derivative of sine is a cosine. K B sine 0 minus, hey, cosine. This gives me 0. Oh, cosine, sorry. KB cosine 0 minus the same thing, no? Cosine 0 is equal to 2m beta over h bar squared times 0. So I'm also good with that. All I'm left with is the boundary condition at the end. I need B sine of KL to be 0. Therefore, KL must be n pi. If KL is n pi, and K is the square root of 2me over h bar, so E is going to be h bar squared. Instead of K, I can write n pi over L, right?
How do you assume that from the equation in the right? That's
B is equal sine KL, right?
B is equal sine KL.
Hi. The boundary condition here is that this, when x is L, is going to be 0. So B sine KL is 0.
It's not from the equation of the right. The equation of the right give me nothing.
This?
No.
Nothing.
No,
You
this
find
gave me
that
nothing.
0 with 0.
Yes. Wait. Okay. We assume this from the borders in the right.
And the boundary condition on the right, yes. And get this on the boundary condition on the right or left, it will give you the same.
Yes.
Therefore, KL is n pi. Therefore, K must be n pi over L. I also know that K is square root of 2me over h bar. Therefore, I can extract E and say that E is h bar squared times n pi over L squared divided by 2m, right? Let's write it a little nicer. E odd would be n squared pi squared h bar squared over 2m L squared. Beautiful! But wait a second. The size of the well here is not L, it's 2L. So let's write here 2L squared and multiply by 4.
Why? The 2L, I understand why multiplied by.
No, what I got here, I multiply and divide it by 4. If I write this a little nicer, I get this, correct? You see this and this are the same?
Yes.
And I'm saying this reminds me of the solution of the infinite potential well. I want it to be more relevant to our case, so I can multiply by 2 and multiply by 4 here. Now, why would I do that? Well, here he shows again what's the meaning of all this. Interpretation of the odd parity, I get this, which is this. These are the even-numbered eigenenergies of an infinite potential well of length 2L. Meaning, instead of putting 4 here, I'm going to put 2 here. So the odd solutions of this case are just like the even solutions of the infinite potential well. That will be here. Okay? Now I can see that if I take beta to 0, it does not affect these at all. This wasn't affected by beta. It will affect this, right? What happens if beta goes to 0 and if beta goes to infinity? When beta goes to 0, so the solution, the thing we had before, was the beta tangent KL. How did we get those Zn before? We said it's the solution of tangents KL is equal to basically beta over K times something. This would be it before.
KL.
It's cotangent. If beta on the top, it's cotangent.
So cotangent KL is minus m beta over K h bar squared K, and here you're saying it's cotangent. Good. Now what happens when beta goes to infinity?
Cotangent goes
To 0.
Well, not true. He talks about it here.
It's going to be phi n.
Good, good. If this goes to infinity, cotangents is
Right, the sign has to vanish, so it's
a cosine over sine. It needs to be something over 0. So sine needs to be, so KL must be n pi. What do you get here? These are the solution, right? This is the solution. If instead of my Zn here, I write n pi, then I get here again the case of infinite potential well. It's like splitting it into two infinite potential wells.
if you're vanishing the delta, right?
Yes.
So you're vanishing the.
So what would I get here? I would get here my solution here would be n squared pi squared, which is just the usual energies of potential well of size L, not two L's. I will get here signs and here signs. Separate from each other. It's a little confusing. The important part for me here as teacher was not this specific potential, but more the approach of assuming wave functions are odd or wave functions are even, and solving through that. Now let's closely look at the homework. The homework should be very easy. You always suspect when a TA says that. But it's basically what we did here. Not very different. We have a square well. We're going to have here a square well and try to finding graphically. Here is finite on both sides, okay? And the energy is going to be negative. So you're going to have a well like this. Here V is 0 and here V is minus V naught. And the energy is going to be here. We're going to try finding a bound state. And one can prove that, as I said before, for any finite potential well, there is at least one bound state. Then you're going to have half infinite potential well, which is exactly what we solved. The only difference is in how do you define the potential? From what I remember, I did it here 0 and here is plus V naught. Here the homework, this is minus V naught and this is 0. So the energy is going to be negative, and you need to make sure that you keep the minuses correctly. Find the condition on V naught, so there will be more than one bound state, etc. Then you're going to have a delta well, infinite well with delta in it. It's exactly what we did, and a pair of delta wells is going to be even more fun. We have two deltas. Have fun. Do you want me to start solving this case? We still have 5 minutes. I can start solving this case. No. Oh, and last week you did when the energy was higher. Now when the energy be inside it. Okay, maybe it's not that easy. Let's decide that number 5 will be optional, okay? We'll discuss that. Maybe it is. I don't know. What do you think? Should we define it as optional or not? I'm debating if I should define 5 as optional or not.
Optional. Optional is also always.
Yes, optional?
Optional. I'm the only one who told it optional.
Okay, 5 will be optional.
Thank you.
מה? בסוף זה משנה במבחן.
כן.
אני אעשה אותו, אבל זה טוב לי עדיין שהוא.